Let's look at another example involving the Lagrange multiplier method. What we find when we utilize the Lagrange method is that we have a set of necessary conditions. So the technique differs somewhat from the second partials test, but we find it to be very useful because we can actually optimize relative to constraint conditions. So in this case, we find the dimensions of the right circular cylinder with volume V sub 0 cubic units, where V sub 0 is fixed, and we would like to minimize the surface area. Okay, so the right circular cylinder, again, has this form here where we have the top and the bottom and the lateral area. So when we want to minimize the surface area, the lateral area, as we know, is 2 pi RH, where R is the radius and H is the height. And then, of course, the top and the bottom are just circular discs. So we get 2 pi R squared, that is 2 copies of the area of the circle. So that gives us the actual surface area. And then the constraint is that of the volume. The volume, again, is pi R squared H, and that must have value V sub 0. So again, we minimize the surface area relative to the volume constraint. Now, the theorem for Lagrange multipliers says that now the gradient of F and the gradient of G will be parallel. So we'll have the system, that is the gradient of F is lambda, some real number, times the gradient of G. We know that is the condition for parallel vectors. And so the gradients are fairly simple. I've written these with the subscript notation. We'll do the R partial of F and the H partial of F. And then, of course, for the gradient of G, we'll do the R partial of G and the H partial of G. So these are very simple, so they're easy to do. The R partials we're going to have for both of these terms. Again, everything else except for the R is considered constant. So when we differentiate out the R, we're just left with 2 pi H. And of course, when we differentiate here, we have the 2R from the power rule, and that multiplies the 2 pi to give us 4 pi R. And then the H partial, of course, this term differentiates to 0, but then the H differentiates to 1, and we're just left with 2 pi R. So the gradient for F has this form. Now for the gradient of G, again, we use the power rule on R squared, and that just gives us 2 pi RH for the R partial. And then, of course, the power rule on the H, or the special case H, just differentiates to 1, and we're just left with pi R squared. So now, utilizing the equation from the theorem, these two vectors are now parallel. So we simply say that the gradient of F is lambda times the gradient of G. So now what we have in this case is that 2 pi H plus 4 pi R will be the first coordinate of the gradient, in this case, times lambda. So we get 2 pi RH lambda. And now for the second coordinate, we get 2 pi R will be, again, lambda times the second coordinate of the gradient of G, which gives us pi R squared lambda. Now, what you're noticing here is that we've got lots of extra stuff here that we can absorb. So here in the first equation, we have the 2 pi, which is common to both sides, which we can absorb, and that leaves us with H plus 2R equals RH lambda. Not very difficult compared to some of the problems we do, but certainly very important. And then, of course, here, the pi's will absorb. If we factor the pi's, they divide out, and we're left with 2R equals R squared lambda. Now, we always usually have to consider the 0 case for the variables, basically because that delineates itself as a second case. And so what we notice here, if R were equal to 0, then we'd have a very simple setup. For instance, here R equal to 0, we just have 0 equals 0, and lambda is free. And then, of course, again, R0 would imply H is 0. So that's not a very interesting case. We have a free parameter here, and we don't have anything that is of value to us, but we still need to consider it. Now let's think of the case when R is non-zero, and of course we get something of interest. Now lambda will just be 2R divided by R squared because that is defined, and one of the R's absorbed, and we just have 2 over R, which is a well-defined real number for a non-zero R. And when we say non-zero R, basically, we're just saying R is positive, clearly from the context. So now, if we look here, we're thinking, okay, what does the other equation give us? Well, from the first equation here, from our system, we can simply solve for H. So now we just replace lambda with 2 over R, and notice the R's absorb, and we're left with 2H. And now, of course, if we just subtract H from both sides, we get H is equal to 2R. So that's great. So now, of course, we can go back to the constraint equation and solve for R and then for H. I mean, obviously, H is just 2R, so once we have R, we're done. So let's go to the constraint equation. We have the volume is equal to V sub 0, but we know what H is, it's just 2R. So now we have what 2 pi R cubed is equal to V sub 0. And now we can isolate the cube term or the R cubed term. And of course, that will give us V sub 0 over 2 pi. And now take cube roots. R will be V sub 0 divided by 2 pi to the 1/3 power. So that's really interesting. I mean, we've got a more flexible problem because V sub 0 can be whatever we need it to be, depending on the problem we're solving. And then, of course, 2 times that, 2 times this cube root will just give us H. And as I've written here, therefore, these dimensions provide the minimum surface area as desired. So again, the Lagrange method is a little bit different, but as I said before, very useful. And you might be interested in saying, well, okay, so what is that minimum surface area? So we know that F represents that. So we can just go to the equation for F and replace the R and the H with their quantities here. So in the first case, the 2, of course, comes from here, the H, and we, of course, have the cube root expression for both R and H. And then, of course, in the top and bottom, we're just squaring the R, so we square the cubic term here. But now, of course, again, we just have the square of this, so we have V sub 0 divided by 2 pi to the 2/3 power, and then, of course, a 4 pi factor, and then, of course, we have 2 pi times the same thing. So I'll factor this, even though you don't really need to do that. Obviously, 2 pi times the V sub 0 divided by 2 pi to the 2/3 power is common to both. So that just gives us the common factor times 2 plus 1, or just looking at it and saying 2 pi plus 4 pi gives us the 6 pi. And again, that would be another way of looking at it. So the minimum surface area for this particular problem, we get to be 6 pi times the 2/3 power of V sub 0 divided by 2 pi. And we are done.